In the last several lectures, we looked at a bunch of new ideas, right? Derived several new formulas, several new counting methods. But it was all very theoretical, and we were focused mostly on how can we answer these questions. So in this lecture, we're going to look at some specific examples, right, and see the kinds of situations where we could apply those ideas. So I've got kind of a straightforward one here to start with. We have a gear that has 10 spokes on it, each of which for some reason has to be assigned a different color. And I want to know how many ways there are to do this. Well, gears and things with spokes are round, right? So I have a round object here, and it's got these spokes or cogs or something distinguishable on them, and it goes all the way around here. And there's 10 of them, and I want to know how many different ways can I color these things. Well, this is a pretty straightforward application of our method for counting the number of permutations of objects, the colors in this case, that are being arranged in a circle. So n is going to be 10 here, right? Those are our spokes. And our formula for doing this says that the number of permutations is n minus 1 factorial. Well, n minus 1 clear is going to be 9, right? So this is 9 factorial. Now you go to your calculator. My calculator tells me that this is 362,880 different arrangements of these colors. So I have a slightly more complicated situation here. We're doing some wedding planning, and we're specifically thinking about the wedding party. That's the dinner that takes place afterwards. And we know that the caterers that have been hired are going to have a selection of 4 appetizers and 6 entrees, and that there's going to be 25 guests, including the bride and the groom. What I want to know is how many different possible menus can the caterer end up seeing? Right. So, how are we going to do this? Well, this is clearly a situation where we're talking about a combination, because the caterer doesn't particularly care who orders first and who orders last, and we have repetition being allowed here. It's not likely, but it's possible, for example, that all 25 people would order the same one appetizer. Right. So this is a situation where we're looking for the number of combinations with repetition allowed. But we have two different things being chosen. Right? We have the appetizers and entrees. So what we're going to do here is we're going to use our new formula for combinations with repetitions, and we're going to combine that with the multiplication rule. Right? So what we're going to do is we're going to find the number of possible appetizer selections. Then we're going to find the number of entree selections. Then we're going to multiply them together. We're just going to straightforward application of the multiplication rule to get the final result. So, how are we going to do this? Well, let's pull out the numbers here, right? Remember that in the formula, n is the number of things that we have to choose from. So when I'm doing the appetizers, n is going to be 4. When I'm doing the entrees, n is going to be 6. And r is the number of things that we have to choose. So we have to choose 25 of each. Now remember, I'm going to write this off to the side here. The formula is n plus r minus 1, choose r. It's now I can put my numbers in. Right? This for the appetizers, this is going to be 4 plus 25 minus 1, choose 25. And for the entrees, this is going to be 6 plus 25 minus 1. Whoops, excuse me, got a little sloppy there. 6 plus 25 minus 1, also choose 25. So this is 29 minus 1. Yes, yeah, 29 minus 1. This is 28, choose 25. And over here, this is 30, choose 25. And if you get out your calculator, I'm just a little new to the formula, so let me write this out. This will be 28 factorial over 25 factorial times 28 minus 25. That's 3 factorial. Over here we'll have 30 factorial over 25 factorial times 30 minus 25. That's 5 factorial, so what do we get? The first one isn't too big. This is 3,276. The second one here, this is 142,506. Just barely ran out of room. If you multiply these together, what do we get? We get 4, 6, 6, 8, 4, 9, 6, 5, 6. Obviously, I did this in advance, right? So I'm just reading the number from my notes here. So what is this? If I put some commas in, there you go, 466,849,656 possible menus that this catering company could have to prepare. So I've got one more here. How many different products of prime numbers equal 3,960? Okay. Well, Um, the first thing I need to know is I need to know the prime numbers that I need to multiply together to get 3,960. So we need to break this thing down into its prime factorization. And let's see, how are we going to do that? Well, I'm just going to go old school. Let's do a tree diagram here. This is 396 times 10. 10 is 5 times 2. 396. Let's see, 2 goes into 396. It'll be 396 divided by 2. That is 198. Then we can do this again, right? 2 also goes into 198, 99 times. Good. Now I'm squared away. 99 is 9 times 11. 9 is 3 times 3. Good. So I know the prime factorization now. 3,960 equals, I've got 3 2's, so it's 2 to the third, times 2 3's, that's 3 squared, times 11. I wrote this out the way we usually do. It's kind of a habit to do this with exponents. But let me actually write this out all the way. 2 times 2 times 2 times 3 times 3 times 11. Now, we know, I talked about this earlier in the class, we know that the prime factorization of a number is unique. So that's the only list of prime numbers whose product equals 3,960. And to get 3,960, I have to use all of them. So essentially, this question is asking how many different ways are there for me to rearrange these 6 numbers, right? Now, we do have a little issue here. Some of these numbers are repeated, and they're indistinguishable. We can't tell either of the 3's apart. We can't tell any of the 2's apart. So to do this, I'm going to use our formula for finding the number of permutations of a set that has some groups of indistinguishable objects in it. So the number I'm looking for here is going to be 6 factorial divided by 3 factorial, that comes from the 3 2's here, times 2 factorial, which comes from the 2 3's here. And if you want to be super complete, yeah, okay, you could put 1 factorial in there. I usually leave it out. 1 factorial is just 1. That doesn't add anything interesting to the result. All right, so let's see if I can do this without my calculator here. This is 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. That's 6. 2 factorial is just 2. So that means I get to cancel out the 6 and I get to cancel out the 2, and all that's left is 60. That's the number of different arrangements of prime numbers whose product is 3,960. Okay, so that gives you a better idea, I think, of how these formulas that we've been talking about can get used, right? If you're working on the online classroom, jump in and take a look at those. You'll see a bunch more examples worked out there for you if you need to see some more. We do have one more lecture to go in this section. We're going to look at a specific type of question called a Diophantine equation. And that's an equation whose solutions have to be integers. And these counting methods that we've been talking about are going to give us a way to be able to look at one of these Diophantine equations and know up front how many solutions it has.